Yeah, good morning, students. Welcome to our webinar session. So today we'll discuss the second chapter, ray optics. Right. In this chapter, we are going to discuss with the properties of light ray, right? And this light ray has the properties like reflection, refraction, dispersion. Along with that, some image formation using plane and curved surfaces like lens and mirrors, and also some optical instruments, construction and working of optical instruments like microscope, telescope, etc. as per our syllabus, and also some human eye related. Right? Meanwhile, we are going to discuss the applications of these phenomena like formation of rainbow, etc. Right. So now we'll start with some points about the light. So light is a form of energy which is causes the sensation of vision. So what does it mean? That if this light is not there, if the light is not there, then what happens? The things that we cannot see, that is what sensation of vision. And it not only makes the things to visible, but also increases the temperature and exerts the pressure. See, we need to learn these things about the light, right? So light not only uses to see the objects, also to increase the temperature and pressure. And everyone knows that light travels with the speed of 3 into 10 power 8 meters per second in the air or vacuum. Now, the first and foremost property of light is reflection. When a light ray strikes the boundary of two media, such as air and glass, a part of light is turned back into the same medium, and this phenomenon is called reflection, that you have learned in lower classes. That is 9th, 10th standard, you have learned this. Okay, so reflection is the basic property of light. So whenever it is incidence on the boundary, means on the surface, then it comes back. So that is called reflection. And here we'll see how the things are going to happen when the light ray is incidented on the surface or interface. See here, the incident ray, reflected ray, and the normal drawn to the surface lie on the same plane. This is very, very, very important law of reflection, that observe this. This is a plane. This is a surface, right? On this surface, when the light ray is incidented, with a certain angle with the normal, this is normal, right? So this normal is always perpendicular to the surface. Okay, both surface and normal always perpendicular. Now, with the normal at an angle I, the light ray is incidented, then originally the light ray has to go in this direction. But due to the property of this light when it is incidented on this reflecting surface, then it comes back into the same medium, travels into the same medium, and this ray means after incidented this surface, the light ray is named as a reflected ray. Reflected ray. Okay, so all these three, that is incident ray, normal, and reflected ray, these three lie on the same plane. This is the law of reflection. So angle of incidence indicates with the I, and angle of refraction denotes with the R. So both are equal. Both are equal. Okay, and the angle of deviation indicates with the D is equal to 180 minus 2I. Look at the diagram here. Originally, the light ray should travel in this direction as indicated with the dotted line here. So the angle between this means angle, total angle will be 180 degrees, right? So total 180 degrees. And the light ray is reflected from this on the surface. And what about this sentence? Angle of incidence is equal to angle of reflection. Means I is equal to R. So both will be, let us take I is equal to I and R is equal to I. Then both are same. Then let us take it as a 2I. And total angle is 180. And this angle between the incident ray and reflected ray is 2I. Then how much is remained? That is 180 minus 2I is remained. What is this? Angle of deviation. Means at what angle the light ray is deviated to the original direction. So this is the original direction of the light ray, but instead of that, it is reflected like this. Then this angle, the angle between original direction to the reflected direction, then that angle is called angle of deviation. So how much it is? 180 minus 2I. Condition is 2I means what? Here I and R same. Clear? So this is what about this one. And here is one more point is the glancing angle. Yeah. The glancing angle is the angle between the incident ray and the surface. This is what glancing angle. But we need to consider only with respect to the normal. I means angle of incidence should be taken only with the I. Now for the normal incidence, the deviation is 180 degrees followed. See, for normal incidence, for normal incidence, the deviation is 180 degrees. Okay. And now there are two types of reflections. Right, just now we have seen only one reflection, that is whenever the light ray is incidented on the surface, it comes back. So that phenomenon is called reflection. And those reflections are two types now. See, one is regular reflection, the other one is diffused reflection. So regular reflection can also be called as a specular reflection, and the irregular reflections can also be called as a diffused reflection. Observe the diagram here. Why it is called irregular? The surface is rough or uneven surface. Right? So in this case, what happened? Observe this. Whatever the light rays are incidented, see first ray like this, incidented, okay, the second ray. See, observe these three are parallel before reflecting. These three are parallel. Once they are incidented on the surface, uneven surface, because of this uneven surface, the light rays are reflected with different angles, different directions. So this type of reflection is called diffused or irregular reflection. And here it is also what regular reflection, as the surface is plane, then reflected rays also in parallel. Okay, so now we'll see refraction. We'll see refraction. The deviation or bending of light rays from their original path. while passing from one medium to another medium. Right? So simply it is a bending phenomena of light ray. The deviation or bending of light rays from their original path while passing from one medium to another medium. Yes, here there are two media, that is air medium is there, and here glass medium is there, glass medium. So there are two media here, right? What is the definition? The deviation or bending of light ray from their original path while passing from one medium to another medium. So this happens, okay, the deviation happens only when the light ray travels from one medium to another medium. Okay, so this bending occurs only when the light ray travels from one medium to another medium. So this is called refraction. So that bending is called refraction. Observe this. In this diagram, there are dotted lines over here, dotted lines. So dotted line is the original direction. Originally, the light ray should pass in this direction, but as it is entered into the other medium, what happened? The light ray is bent like this. The light ray is bent like this. So this is angle of incidence to the normal, and R is the angle of refraction. It's making angle with the R, normal here. Okay, R is the angle of refraction that light ray is making angle with the normal. So this is the angle of refraction. Right? If you go further, see, refraction happens only when there is a change in medium. So that was happened here. So that's why the light ray is bent. Here we considered a glass slab like this, means a piece of glass. Then the glass slab has two edges, upper edge and lower edge, which two surfaces are there. Okay, so the light ray travels inside the slab or glass plate. Okay, so then at the another edge of this glass plate, what you found that again from this point it is entering into the air medium, another medium. It is entering into another medium. Right? So while it is entering into the one medium to another medium, that is glass to air, again the bending is occurred. Again, the bending is occurred. So what you understood with this is, whenever the light ray travels from one medium to another medium, the light ray bends. And this bending phenomena is called refraction. And here, look at this diagram. At this point, this ray is called emergent ray, and this is called angle of emergence. Right? And one more condition is condition for no refraction. Condition for no refraction. See, what is that? Condition for no refraction means at what conditions there will be no question of refraction. That is very important. Means at what point, means at what angle, if the light ray is incidented, then there is no question of refraction. What is refraction? Bending. So the bending will not happen at what condition is asking. See, when the light ray strikes normally at the point of incidence. Normally means perpendicular to the surface. Perpendicular to the surface. Normally at the point of incidence, it does not deviate from its path. That is, it suffers no deviation. So, whenever the incident ray is making angle, any angle to the normal, then only all the, it's moving from one medium to another medium, refraction takes place. But without any angle, if the light ray is incidented along the normal, then there is no reflection or refraction. Okay, optically rarer medium air, so the light ray is falling along the normal. Then along the normal, if it is incidented, see inside the glass, straight away it is moving, there is no bending at all. Right? So what you understood? So in this case, the angle of incidence I and angle of refractions both are same, both are equal. Okay, so angle of incidence and angle of refractions both are same. I hope you understood this point, right? So now we'll move on to the next one, that laws of refraction. Laws of refraction. Incident ray, refracted ray, and normal always lie on the same plane. The product of refractive index mu. Let me explain this refractive index later. And the sign of the angle of incidence at a point in the medium is constant. This is called Snell's law. This is called Snell's law. So all these things already you have studied in the lower classes. Just for revising these as per in the afternoon session for competitive point of view, we need to learn these things bit deeper. So that's why the Snell's law here. Look at this. Light ray is incidented, making angle with the normal I, and incidenting from one medium that is indicated with the n1. Some books with a mu1, okay, mu1, and incidented. And as there is a change in medium, the light ray is bent, and this bending ray is called refracted ray, and this is making angle R in the other medium whose refractive index is n2. This is n1 and this is n2. So refractive indices I'll explain, right? So here just it's a law of refraction concept we are discussing here. So what is that? It is the product of refractive index of a particular medium and the sine of the angle of incidence. Angle of incidence is I. Then sine of angle of incidence means sine I is multiplied with the mu, where mu is what? Refractive index of a medium. So that is equal to constant. This is what is the Snell's law. Means, look at this, mu1 sine I, mu1 sine I. Look at this diagram. The light ray is incidented through the medium n1. I told you, no, sometimes it will be n1 and sometimes it will be mu1. So for understanding, I've given these two. Don't be confused here. So some books will refer with the n1. So whatever it may be, it is a refractive index. So refractive index of this medium is mu1, and here in this medium the light ray is making angle I. Then mu1 sine I is equal to, is entering, refraction is taking place in another medium whose refractive index is n2, and here it is making angle R. So mu2 sine R. So the ratio of these two gives constant. Any value of these two ratios. For example, the light ray is incidented at the angle I1, and it will reflect with the refract with the R1. If the angle of incidence is I2, then angle of refraction will be R2. If the angle of refraction is I3, the angle of refraction will be R3, and so on. Angle of incidence is In, angle of refraction is Rn, and the ratio of those two always be constant. This is Snell's law. This is Snell's law. Okay, that is mu2 by mu1 is equal to constant. And I told you the refractive index. So refractive index indicates with a mu, and it may be defined as very important that we should learn. So here comes the basic information about how the light ray bends. Okay, refractive index, it may be defined as the ratio of velocity of light in free space to the velocity of light in given medium. So simply it may be defined as the ratio of velocity of light in air to the velocity of light in medium. Velocity of light in air to the velocity of light in medium. Right. So everyone knows that velocity of light in air is how much? Is a 3 into 10 power 8 meters per second. That is fixed. That is constant. That is in vacuum or free space, right? Free space is given. Indicates with the C here. C, letter C here. And the same light, when it is incidented other than that air, so definitely that velocity changes. Definitely the velocity of the light changes, right? For example, we know the value of velocity of light in the air, that is fixed one, 3 into 10 power 8 meters per second. And the same light is incidented other than air, for example, water or a glass, definitely it will be less than the original, less than the air. So that ratio gives velocity of light in air to the velocity of light in medium. That ratio gives the refractive index of this particular medium, means in which medium you are sending the light ray. So in which medium you are trying to send the light ray. So that medium's refractive index you can calculate. So refractive index is a physical quantity that explains about the nature of the medium, type of the medium comparing with the air, whether it's a denser medium. So definitely it's a denser medium. So air is a comparatively it's a rarer medium. Okay, so denser, rarer, that the terms that you should understand. Okay, right. And this refractive index is a scalar quantity and it has no units and dimensions, because upper part is velocity, lower part is also velocity, meter per second will cancel, so there will be no units for this. Okay, so no units means no dimensions. So it's a scalar quantity. Now from means the same concept if we treat in terms of electromagnetic theory. Okay, I'm repeating the same concept, same discussion. This is refractive index discussion. If we made in terms of electromagnetic theory, so look at this. If epsilon naught and mu naught, epsilon naught and mu naught are the permittivity and permeability of free space. Epsilon naught and mu naught are the two physical quantities, permittivity and permeability, that gives about the transmission of the either charges or light, sound, whatever. See, that depends. It's a property of a medium. Okay, the permeability and permittivity is purely related to the media. So based on the type of medium, these permittivity and permeability values changes. So it's a free space. We are assuming E naught and mu naught are values for the free space. Similarly, epsilon and mu, are the permittivity and permeability of given any medium, any medium. Okay, see, look at this. In this case, velocity of light in free space, velocity of light in medium. The same thing, permittivity, permeability of a free space, and permittivity, permeability of a medium. Then the refractive index of that particular medium is expressed as, now look at this. We know the formula, mu is equal to C by V. Here is mu is equal to C by V. Now we have a relation for the C is equal to 1 by under root epsilon naught mu naught. So this is the C value in terms of free space. And here it is in terms of any medium. So 1 by under root epsilon mu. So what happens here? It will become under root epsilon mu by epsilon naught mu naught. That gives under root epsilon r mu r. Here these two are called relative. These are called relative permittivity and relative permeability. Relative permeability. Okay. So all these relations that you should understand. Right. So here is one more concept usually appears the exam. Mostly it is a 2 marks question is there. Optical density. Optical density, the property of a medium to slow down the speed of the light is called optical density. Yeah, density that we know. What is the density? Mass per unit volume. Mass per unit volume. So here, which mass? Whose mass is this? Here, it is related to the medium. For example, In an air medium, the light ray travels with the constant velocity. Of course, it's a more velocity, 3 into 10 power 8 meters per second. Right? When the same velocity, when the same light is incidented other than air medium. Remember, other than air medium through which the light can pass through in such media like water, glass, any chemical, any liquid, any chemical, like, okay. So all those are visible. We can see those media. Means what? Automatically, those media are denser than the air. If density is more, density means what? Mass per unit volume, mass of individual particles in the medium. So if those particle density is more, then the light ray cannot travel freely as much as in the air. So definitely that light ray makes a number of collisions with the particles of the medium, then the velocity decreases. So that's why it is this property of a medium. Optical density means what? The property of a medium. So it is related to medium only. That slow down the speed of the light is called optical density. So a medium of higher refractive index has more optical density. Means whatever the medium is, if that has more refractive index. What is refractive index? Just now we discussed. It is the ratio of velocity of light in A to the velocity of light in medium. So then if that medium has a high refractive index, definitely that has a more optical density. Now, see, as you know that mass density, this thing you know that you learning from long time. So that mass density is what? Mass per unit volume of the substance is called mass density. And there is no direct relation between this mass density and optical density. Both are quite situationally different. Okay, situationally different. See, this mass density gives only the amount. Okay, right. And see here, optical density gives the velocity of light ray, traveling through the medium. So here matters. But directly there is no relation between optical density and mass density. The question is only for confusion question, and you get clarified what is optical density and mass density. Similarly, in electricity also, charge density is also there, right? So now we'll move on to the next one, that critical angle. Very critical part it is. So it is a critical angle, indicates with the C here, when a ray of light passes from denser medium to rarer medium. Okay, so up to now we discussed the light rays traveling from air to other medium. Now just we have started discussing this with the denser medium to the rarer medium, and the angle of incidence means at what angle we are incidenting on the surface, right? Actually it is not surface, it is called interface, because both the denser medium and rarer medium are in contact. Means one line that separates the two media is called interface, right? Now at that interface, if you are incidenting a light ray, then that angle of incidence in the denser medium only, because the light ray started from the denser medium. Okay, the angle of incidence in the denser medium such that if the angle is a refraction, means moves into the other medium, refraction, if that refracted angle is 90 degrees, then that incident angle is called critical angle. You see how critical is this? Yes or no? Of course, you might have studied this in 10th standard, right? So here critical angle means this critical angle is related to incident angle, right? It is incident angle. Critical angle is related to incident angle only, right? So how we can define this? When the light ray is incidented from denser medium and reaches the interface over here, okay, reaches the interference at this point, then what happens? The light ray bends. Observe this. While it is entering from one medium to another medium, see denser medium, rarer medium. Entering from denser medium to rarer medium, what happened? The light ray bent. Okay, so here I and R, okay, here. Now see the next arrow is passing through the denser medium and the incidented over here. Look at this. The refracted ray, if it is passing through the interface. Interface means what? The line that separates the two media is called interface. Then that angle of incidence, is called C, critical angle. Have you seen? Here it is indicated with the I here, because the refracted ray is not moving along the interface. But at what angle the light ray is incidented such that angle of refraction is 90 degrees and such angle of incidence is called critical angle. Critical angle. And the next ray we'll discuss. So applying the Snell's law for this, Snell's law we have seen that what mu1 sine what that refractive index of the medium is multiplied with the sine of the angle of incidence that we have discussed. The same thing here. Mu d means refractive index of the denser medium multiplied with the sine incident angle. In here incident angle I became what? I became C here. So incident angle sine I is equal to refractive index of the rarer medium. Refractive index of the rarer medium. And again sine, and what is the angle with the refraction is 90 degrees. Originally what was the equation? Mu1 sine I plus mu2 sine R. So sine I is C and sine R is 90 degrees, and mu1 is the denser medium and mu R is the mu2 is the rarer medium. So this is an expression that sine 90 is 1 here. So mu R is equal to mu R. It is refractive index of denser medium with respect to the rarer medium is 1 by sine C. And sine C is equal to mu rarer by mu denser. The refractive index of rarer medium to the refractive index of denser. And the relation between the velocity and here is a refractive index. So look at this, both are right inverted here. So this mu is rarer here and V is denser and lambda is also denser. So observe this equation. So in the afternoon we are going to solve the problem from this. And now we'll move on to the next concept is total internal reflection. This is also studied in the 10th standard. That total internal reflection. Here see that when a ray of light passes from denser medium to the rarer medium, such that the angle of incidence I, if it is greater than the critical angle, then that light ray is totally comes back into the same medium. Then this this is according to law of reflection, and this phenomenon is called total internal reflection. Look at this same diagram. If it is the incident light ray is incidented along the normal straightaway perpendicular to the interface, then what happens? There is no bending. There is no bending. See, it is even though the two media are there, that is N1 and N2, two different media are there. So even though we discuss, when the light ray is traveling, incidenting perpendicular to the interface, then there is no deviation. And now look at this, with the normal, the light ray is incidenting with an angle θ1, then the refraction takes place with an angle θ2. And now see the third ray is, the light ray is incidented such that the angle of refraction becomes 90 degrees, then such angle of incidence is called critical angle, right? Now if you see, if we incident the light ray more than critical angle, more than, observe that these three rays here, angle of incidence is slowly increasing. Here θ1 is there, here θc, and angle of incidence is increasing here. So if that is greater than critical angle, so definitely it is a greater than critical angle, then it is not entering into the other medium. See, look at this, at critical angle itself, it is traveling along the interface. If you increase the incident angle, then what happens? It will come to same medium. It will reflect into the same medium. And this phenomenon is called total internal reflection. Internal means what? In the same medium. Total means what? Whenever means a particular frequency or particular intensity of light if you send over there, so there is no deviation. You see in this the energy of the particular light cannot absorb or refract into the other medium. So the same amount of energy will be comes to the same, reflects into the same medium. So this is called totally internally reflection. Okay, total internal reflection phenomenon. See here in total internal reflection, there is no loss of energy. Just now I told you, no. So what is the advantage of this is why it is called so called? It is total internal reflection means what? Whatever amount of light ray if you send, okay, at an angle greater than critical angle, then what happens? The same amount of light ray will reflect into the same medium, and there is no question of either absorption or refraction, either absorption or refraction by the medium. Okay, the same amount will be reflection, the same medium. That's why it's a name total internal reflection. And examples of total internal reflection in daily life, we use this total internal reflection phenomena. Optical examples for optical internal reflection. Here, optical fiber works on this principle only. Optical fiber. Okay, so this is the latest technology here nowadays. Of course, it started very long back, but it is in this optical fiber communication system. We use this principle only. In this communication, we use laser light. So that laser light travels with multiple total internal reflections phenomena. So it makes internally, you might have studied this about the core and cladding system will be there. So as there is a change in true media of glass material, so whenever there is a change in media, the light ray bends. If the light ray is incidented more than critical angle, it follows total internal reflection. So whatever the light ray we send, whatever the information we send, the same thing can reach the other end without any loss. That's what is the meaning of this sentence, that energy cannot be lost. And this used in diamond cutting that glitters well. Yes, optical fibers can be used in diamond cutting also. And mirages at hot places or at deserts. So this is also reason. Okay, total internal reflection is one of the reasons to form mirages in the deserts or hot places. Okay, mirages means that you know, right? There. So now we'll move to the next is how the mirage will be formed. Means what is the role of total internal reflection for the formation of a mirage? It is the part of your syllabus, and mostly the 4 marks question will be asked from this formation of a mirage. Okay, right. So mirage is an optical illusion in which the light rays are bent to produce a displaced image of distinct object. So mirage is an illusion. Okay, when the light rays are bending to produce, displace the image, appears that the image is displaced. Right? So what is happening here? We'll see. Now mirages are formed due to total internal reflection phenomena. Right? And on hot summer, the density of air is less. The density of air is less near the ground due to heat, so that the refractive index is smaller than the cool air. Yes, here comes the relation that we should understand. Refractive index means what? It tells about the density of the material. Density means what? Ratio of velocity of light to the velocity of light in the medium. So velocity of light obviously smaller in the denser medium. If density is more, the light ray cannot travel more fast. So during hot summer, particles having more energy in the form of heat, right? So due to that density, the closeness of the particles will be very small. Means they are with that energy. What happens? The energy means what? Heat energy. So with that heat energy, what happens? These particles moves means that closeness will not be there. So density will be small. Density will be very small. So as see, usually what at what situation it happens? Near the surface of the earth. Near the surface of the earth, because the earth gets hotted during summer. Earth gets too much hot. So the atmosphere which is near to the earth, getting due to this hotness, the density will be decreases. Density will be decreases. So density of air is less near the ground, because due to the hotness, I told you, due to the heat energy, the particles moving upward, means lightweight. Okay, weight will be light, then what they will move upward, and due to heat and yeah, so that the refractive index will become smaller than the cool air. Refractive index will be smaller. Now refractive index is smaller means what it says, right? So when the air is stationary, the optical air is stationary, the optical density at different layers of air increases with the height. So near the ground, heat will be more, then the density will be small, and as you are moving uh, away from the earth, moving upward to the earth, then in the atmosphere there are layers of atmosphere forms as per the density. So the air, the optical density at different layers of air increases with the height. Okay, density increases. Near the ground, density is small. As you are moving upward, okay, upward, then density increases. So if density increases, velocity of light decreases. Velocity of light decreases, right? Hence the light rays coming from tall bodies, means while you're watching, you're looking at a long tall bodies like a tree, right? Yeah, big trees. While usually you can see those things while you're traveling on hot summer, um, through cars and all. If you see on the roads, that those are the mirages only. So on the roads, you can see the image of the trees. Okay, so that appears, means there it shades actually, but it appears as in some water is poured on the roads like. So hence the light rays coming from the tall bodies appears like a bending away from the normal and undergoes the total internal reflection. Here comes the picture. Usually, yeah, here hot summer, near the surface what happened? Hot air. Here the density is low, then the velocity is more, and while moving upward, the air is cooled, then the density will be more. So the light ray moving from one part to the another part, one part to the another part, means between this ground to the certain height, means at this high side, then medium is different, refractive index is different, then velocity is also changes. Why these rays are bending here? Because whenever the medium is changed, the light ray bending. This is the reason. Whenever the light ray is, whenever the medium is changed, the light ray bends. And see, as actually the person is appearing, means looking this area. It's not original actually. It's not real actually. It appears that the sight is in this direction. The sight is in this direction, but the light rays are coming like this. The light rays are coming. The image is reflected ray from this object is entered in this direction. To the eye is entered in this direction. So eyesight direction will be in this direction. So the person can see the image over here, because the distance is very long. Then it appears like that shade, and this area is called mirage. Originally it's not real. It's not real. Okay, so this is called mirage. Now here a very important point is rainbow. So this is also the part of total internal reflection. See, all these are, see, a formation of that mirage and the rainbow. So So all are very, very, very important as per the IPA point of view. So you should practice them. Okay. So here is the rainbow concept. So rainbow, it is a multicolored arc that appears, right? That appears in the sky opposite to the sun on a rainy, okay, days is called rainbow. It is the combined effect of, see, the three parts are there, that is dispersion, refraction, and total internal reflection of sunlight by spherical shaped water droplets, right? So these water drops acts as a small prisms. Okay, so prism concept we'll discuss now. So prism and causes the dispersion and total internal reflection of sunlight to form rainbow. So here is what rainbow is, what multicolored arc that appears in the sky in the opposite to this sun. Remember, it's always look at the diagram over here. Opposite to the sun, it should be raining, means in the sky, and both the things should happen, that raining and sun. Like usually the people cannot see because the rain occurs only when the sky is cloudy. But occasionally what happens when both, means one side of the sky is with the sun, the another side of the sky with the clouds, and near the clouds the rain may come, and here this sunlight is incidented on those raindrops, and the person from the earth can see that beautiful dispersion of light ray. Actually from the sun the light ray is white light. Okay, in detail we'll discuss this, but here it is only what rainbow formation. Look at this, white light is coming out from the sun. Let us take this the AB, right? See, traveling in one medium, and the circle is what is a water drop. When the light ray is incidented on water drop, see, observe the medium is changed. The light ray is traveling from air and it is entering into the water medium. Then medium is changed, then what happens? Light ray bends, and here is given one point is water drops acts as a small prisms. Water drops acts as a small prism. What is the nature of prism? When the light ray is incidented on that, it gives 7 colors. That is called dispersion. It gives 7 colors. So this water drop behaves as a prism. Then when the white light is incidented on it, then it disperses into the 7 colors. Observe this. And when these 7 colors is formed from one internal surface of the sphere to the another internal surface, there what happens? Reflection takes place. This is called total internal reflection. Why it is totally internally reflected? Because these 7 colors incidented on the interface. What is interface? Of water and air. Water and air. Then at an angle which is greater than critical angle. Which is greater than critical angle. Then what happens? All the light rays will reflect into the same medium. So no ray is coming out. Observe this. So all the rays are reflected into the same medium and incidented other place of the sphere, water. Okay, so now this angle is not related to the total internal reflection or critical angle. So just like that, they are coming out, means just medium is changed here from water medium to the air medium. Then refraction, the bending takes place. Observe here inside the water drop, bottom one is violet and the top one is red. But the moment it is reaching to our eye, upper one is red and bottom one is white. And these beautiful 7 colors that we named it as a rainbow. So this is what is the formation of rainbow. right? So now there are two types of rainbows. So as per our syllabus, the two cases are there. So this is also one of the important questions. The 4 marks, you practice them, right? Primary rainbow. So if you understood that how the rainbow is formed, okay. So what was that? One dispersion, one total internal reflection, and two refractions. Two refractions. Okay, here at a point B, one refraction is taking, and here at a point D, another refraction is taking place, and at this is the dispersion is taking, and at a point C, total internal reflection is taking. Okay, so keeping that in mind, we'll go for primary, means classification of rainbows. There are two types out there. That is primary rainbow. The sunlight is refracted as it enters. Refraction. Okay, the same the thing we discussed in the diagram just is right up here. The sunlight is refracted as it enters a raindrop, which causes the different colors. That is dispersion. Now these refracted rays strike the inner surface of the drop and gets internally reflected because their angle of incidence is greater than critical angle. Then these internally reflected rays again get refracted at the other side of the sphere. That's what water drop. As the red is less deviated, and the red from upper level drop comes straight to the observer and appears on the top of the rainbow. And as violet is deviated more, and it comes from lower level drops, lower level of the drops, and appears at a bottom. And if this is happened, then this is called primary rainbow. Just now we discussed the diagram that is primary rainbow. And now if you see the secondary rainbow, it's of course it's a rare, and it's you can't see that much clear images for this. It is formed due to double internal reflection of the sunlight. Okay, so double internal reflection of sunlight in the raindrops, hence it appears